Yeah, so these ion pairs turn out to be very important. They're all over chemistry, and it's not very well recognized in the nanoparticle literature. You don't hear much about it. In fact, people only recently moved on from the idea that everything is this type and started thinking about charge balance involving non-stoichiometry of the crystal. And now there's greater awareness that this charge balance with an outer sphere ion is very significant. So we'll take a look at some of those materials now. The other thing that we described last time, which is, I think, a very important principle in this area and is often overlooked, particularly when designing a new direction, is the surface atom density. Okay, the surface atom density of the sort of canonical facets of most of the classical materials is higher than alkanes can pack. Okay, I actually should have included this slide, but on a silicon crystal, on a 1-1-1 surface, 1-1-1 surface has a single dangling bond that is orthogonal to that facet, and 3 bonds into the crystal. That would be the top of this guy there. Those 3 attachment points give you 1 bond orthogonal to that facet. And on silicon, the proximity of the things that are orthogonal is so great that you cannot put anything larger than a methyl group on a silicon 1-1-1 crystal, or at least with complete coverage. So it's possible to put hydrogens in all of those positions, and it's possible to put methyl groups in all of those positions, but ethyl is too large. You end up with missing groups. And in fact, the hydrogens of methyl groups on a 1-1-1 surface interdigitate and rotate coherently. So they move together. Okay, the rotational barrier of the methyl group on that surface is dictated by steric interactions with adjacent methyl groups. So that's very, very high packing. And you can see silicon is not too far off from the density of all these other materials that are of interest. Okay, so methyl is kind of big. Anything bigger than that is problematic. And that tells you that these types of materials have dangling bonds. You know, the atoms on the surfaces do not achieve coordination geometries that look like small molecules. Okay, they're very different. I find that really interesting, super interesting. That helps to explain these equilibrium constants. Well, constant was measured exactly, but these equilibria here, the binding and displacement reactivity that you see is a function of the way the ligand coordinates the cadmium ion that comes off, but also the way it binds the surface. Okay, that explains why relatively weak bases that are sterically small are effective in this reaction. They pack with higher density because of their size. Tributylamine is too big to do this reaction. Tributylamine binds cadmium oleate. It does not bind a quantum dot very well. Things like trioctylphosphine oxide are way too sterically encumbered to be meaningful ligands for a nanoparticle surface, for any surface. Okay. This observation leads to one more conclusion I want to leave you with, and that's that the packing density is a strong function of the size. And when you consider a competitive binding situation, small molecules will outcompete large ones, even if their bond association energy is weaker. Because you can get 4 to 8 times the number of connections. Right? And so if you just measure in terms of numbers of bonds and their bond association energy, small things with weaker coordinating power can displace big things with a stronger coordinating power. Okay? All right. The other thing that we mentioned was that we introduced this idea of the DLVO theory, which is a description of the attractive and repulsive forces in a electrostatically stabilized colloid. we described the various layers that form around the crystal. But when you have an anion, as depicted here, that's associated tightly with the crystal and an outer sphere cation, you develop a net negative charge around that object. We define something called the slipping plane, which is the amount of solvent and associated ions that moves together with the crystal. So the net charge on this object is defined by that. And that leads to something called the zeta potential. So it's the electric potential at that layer. And when you consider the attractive force and the electrostatic repulsion of two objects with opposite charges, you end up with this pretty interesting relationship that has a minimum. This is a position where the crystals can sort of stay associated with each other weakly. Getting any closer than that, electrostatic repulsion sort of turns on. We said that the zeta potential, which is the magnitude of that electric potential at the slipping plane, is a very, very important parameter in defining the magnitude of that potential, as is the dielectric constant of the solvent. So, yeah. All right. So let's talk about a few examples of these types of things. I'm not going to really get into the diversity really, but slowly but surely there are more and more depictions of this type of stuff. These are my renderings of compositions that have been made in the literature. We're going to talk about amines reacting with carboxylic acids to produce carboxylates and displace other anions, and we could talk also about these ammonium halide complexes and thiocyanate complexes and so on and so forth. So probably the sort of most common presentation of this type of thing that you're going to see is that one takes a standard sample of cadmium selenide. These are carboxylate terminated cadmium selenide quantum dots of the type we talked about earlier. And they're soluble in a solvent like hexane. And then if you take a solution of an ammonium salt, these halide salts, in a formamide solvent, so this is N-methylformamide, you get a biphasic mixture. Those two solvents are not miscible. And if you shake up that solution, you'll find the quantum dots will transfer to the polar phase. Okay, and so there's nothing polar about an oleate chain. And in fact, if you add polar solvents that are soluble in hexane to a hexane solution of oleate terminated dots, they precipitate. So this conversion suggests that the ligand shell has been changed. Okay. Other things like sodium salts, potassium salts will do it, but you have to have an anion that coordinates. Okay. Nitrate is not a very good ligand apparently, and it doesn't outcompete the carboxylate. I find it remarkable that a halide ligand is sufficient to displace a carboxylate ligand. I find that surprising, actually. Part of this reaction also probably involves the ammonium ion and protonation of the carboxylic acid. It may also involve displacement. Sorry, this got cut off. It may also involve displacement in this example here of this drawing. This is a lead chalcogenide crystal. And so you can see lead carboxylate being removed. So, whether or not there's an X for X type exchange, or the halide comes in and removes cadmium oleate from that crystal is not always clear. Making those kinds of determinations is very difficult. What is clear is that you get a solvent change, and you can go and measure whether you see oleates present or not. And it seems there are none in many of these kinds of examples. So these kinds of exchanges are relatively straightforward. And it's not uncommon to have this type of situation. Here's an example of another displacement reaction that we studied in my group for many years and is representative of a long history of this type of thing. It used to be the case that people would take a sample of topo-coated quantum dots and add an amine ligand, like pyridine or something like that, to try and displace all of the topo. And the common commonly reported observation is that removing all of the ligands is very difficult. In fact, that almost all of those attempted exchanges are incomplete. Okay, and it was not clear why that would be the case. A lot has changed since those days, but it still remains the case that it's hard to displace ligands. And one of the explanations for this that we'll talk about is that when you add a neutral donor to a sample of cadmium selenide quantum dots with carboxylate ligands, for example, there are other reactions that can take place, like deprotonation of any associated carboxylic acid. And the formation then of this displaced cadmium oleate, amine-bound particles, and also these ion pairs. Okay, so Peter Chen and my group studied this reaction to death. And the typical result was that you end up with about 15 carboxylates per nanocrystal left over. That's about 10% or so of the starting coverage, 5 to 10%. So you always see this stuff. And the vexing thing about this is, well, you might imagine in the solution of amine, an amine ligand could come along and displace that carboxylate anion and remove that salt. But that was never successful. So another example of this sort of ion pair formation was observed in this reaction here. We talked about this conversion of carboxylate to chloride using chlorotrimethylsilane. And in the presence of tributylphosphine, one obtains a tributylphosphine complex nanocrystal. But the other thing that forms is tributylphosphonium chloride. Okay, so now you have a situation where you have phosphines and phosphonium ions and chloride ligands. And the only way to know that you have this is to be able to distinguish phosphonium from phosphine. And that's not that straightforward unless you have phosphorus NMR. So this spectrum here shows you that the various phosphines present in that sample, they have a couple of different structures. It's not a simple looking spectrum. And a really significant component of that is this resonance out here, which is coincident with the protonation of phosphine in this kind of an environment. Well, maybe just for the sake of discussion, the other thing that's produced in this reaction is a phosphine complex of cadmium chloride. This turns out to be a complex mixture of objects. It's not a simple single structure. And it gives you this broad resonance here. I would say we don't fully understand this thing. And in fact, my belief is that this may involve ion pairing, where chloride comes off of this object and sticks to the particle, leaving behind a cationic counterion. Now, that possibility is extremely difficult to know, to assign. Okay, distinguishing something that's neutral in solution from some ion pairing situation is not straightforward. There is no good way to do that, really. I've thought of some, but it's never really stuck. So we draw this picture up here, but I don't think we really know what that formula is. And I think there are a lot of possibilities that cannot be distinguished from each other. All right, so word to the wise when looking at reactions that people draw, formulas of particles. Life is far more complicated than you want it to be in these materials. And people's understanding of these things is really elementary. Okay. These sorts of materials are very unusual. One of the ways we learned about this phosphonium ion is that if we add dimethyl cadmium to this sample, we can actually liberate methane. It's kind of a fun experiment because it produces cadmium chloride as a byproduct. Right? This is essentially HCl, phosphine, and dimethyl cadmium, making methane and cadmium chloride and phosphine. And that clearly makes this sort of resonance go away. Okay. So we have very good evidence for that. And we also know that if we take cadmium selenide with carboxylate ligands that have a small amount of acid impurity, we could do the same experiment where we add dimethyl cadmium, again, making methane as a byproduct and producing cadmium carboxylate. And it turns out we think that some of these methyl groups actually end up on the particle, or they can, which is kind of interesting. All right, so you can get rid of that stuff if you want, but you've got to go to great lengths. Okay, dimethyl cadmium is no joke, but it's effective in this reaction. So if you do that, then it becomes possible to completely remove the carboxylate ligands, forming this amine-bound cadmium carboxylate as a byproduct and a simple neutral stoichiometric nanoparticle. Now, this object here looks sort of simple on the face of things, but I don't think it is simple. And it turns out that it's very colloidally unstable. Okay, so if you want to make and dissolve a sample of cad selenide quantum dots with primary amine ligands, which are one of the most basic and sterically unencumbered ligands, right? This is a best case scenario for stabilization. You end up with something that is colloidally unstable. If you look at the electron microscopy images of these, you see particles that are fairly not very well ordered. If the amine concentration of those solutions drops below about 100 millimolar, aggregation and precipitation becomes a problem. Here's an NMR spectrum of this type of quantum dot. And in fact, not all of the amines in this solution are bound to the particle. But yet one sees only one set of NMR resonances. And the reason is that the amines that are free in solution and those that are bound to the particle are exchanging more rapidly than the NMR timescale. Okay, so the NMR experiment takes about a second to record the magnetic information of the sample. And in that time frame, the ligands bound to the particle and those in solution undergo exchange many, many times over. So these exchange rate constants or lifetimes are like on the order of a microsecond or faster. Okay, they're very, very fast. So this material is very labile. It is an unstable object. It's possible to take these best case scenario ligands and desorb them completely in vacuum with heat. Okay. All right. So I raised this to make the point to you that the simple L-type ligand stabilized nanoparticle is not very realistic for some materials, perhaps for many. Okay. All right. We don't need to talk about that. All right. So this substance, however, has proven very useful because you can take it and react it with various acids to produce colloids that are stabilized by ion pairing interactions. There's the ammonium carboxylate material that I described earlier. You add a little carboxylic acid and you'll find carboxylate ligands on the nanoparticle surface. Proving that you generate ammonium ion, however, is very difficult, it turns out. How would you do that? The best way that we found was to look at the FTIR spectrum in the region where you see an ammonium vibration. And that ammonium, OH and NH modes are out around 3,000 to 3,500. If there's water in your IR spectrum, you get a big broad band. And in our case, the difference between this ammonium carboxylate and just the amine bound sample alone is really just that little, basically it's a shoulder here between 3,200 and 3,000 wave numbers, which is highlighted in blue. Okay, so that is the ammonium ion vibration. So if you took a sample of this material and put it into an FTIR experiment, proving that you have generated or you have ammonium ions present is not straightforward. And distinguishing between carboxylate that's balancing charge with a cadmium ion on the crystal and one that's balancing charge with an outer sphere ammonium, very hard to do. I see this all over the place in the literature and in talks. People do not know how to distinguish between these two things, and they naturally revert to the simple description, which is not the ion pair, but the simple neutral molecules. Another example of this is phosphonic acid. So phosphonic acids will protonate amines, and you can absorb phosphonate to the particle. Phosphonate can have multiple different protonation states, right? The dianion or the monoanion, they have distinct chemical shifts, and you can see them in the spectrum. These two experiments are interesting because the one on the top is not favorable in toluene solution unless the particle is present. pKa of a carboxylic acid is not low enough to protonate an amine in toluene. It is in water, solvent dielectric matters, and the particle provides that driving force in this case. Phosphonic acids are stronger acids and will protonate amines without the help of a quantum dot. Another very important reaction that you'll find is the reaction of CO2 with primary amines. If you take a bottle of liquid primary aliphatic amine off the shelf in your lab and you take the cap off, you'll find a bunch of white crust in the threads of that bottle. That is an ammonium carbonate salt that forms upon reaction with CO2. Liquid primary amines are used to scrub carbon dioxide out of gases in industry. So if you're trying to take CO2 out of, the methane that you drilled out of the ground in the North Shore of Prudhoe Bay, you scrub it by bubbling it through a solution of ethanolamine. So primary amines react with CO2. They do so if left on the shelf, or in our case, we actually added C13 labeled CO2 to this amine capped particle and produced this resonance out here, which corresponds to the carbonate anion. So this is problematic because most people think, I have this amine bound sample, but they don't consider the fact that their amine contains carbon dioxide. It's not a well-known. I think people, with experience, you learn this sort of thing, but that is ignored, okay, most of the time. These sorts of ions play a really big role in the synthesis of particles and in their stabilization. Okay, so ion pairing is really important, and it is kind of mischievous. People are unaware of how significant it is. They don't propose it, but it's there all over the place. All right. So the last thing I'll say about this is the binding coefficient is surprising. Okay, so when you take a sample of particles like this, so we have, say, cadmium oleate and oleic acid on cadmium selenide, and you add a primary amine to that sample, you make this stuff. And it turns out it's very difficult to remove that carboxylate ion in exchange for a simple neutral donor. Why is that? What is the driving force for that? Right? They're both just, 2 electron donors. One produces a surface potential, the other doesn't. Primary amines are good ligands. They're sterically unencumbered. They're basic. They have about the same basicity as a carboxylate anion. So why is it that this equilibrium actually lies pretty far to the left? And that has to do, I think, with the structure of the facet to which it's binding. So this is, I think we showed this on the first day, this video of this is a cadmium selenide quantum dot of a very typical size in the region that people tend to study. The ligands that you see there are oleic acid ligands, and you'll notice that they are not symmetrically distributed about the particle. And it turns out that there's a preferential binding of those carboxylates to the 1,0,0 surface of that material. Okay. And the reason there's preferential binding is that the carboxylates can chelate. They make multidentate interactions. And in fact, on a nanoplatelet of the type you see here, people have computed the structure of those carboxylates. Notice they've chosen formate here as their carboxylate. look at that hydrogen pointing over at the adjacent carboxylate. Those are fairly close contacts. Putting something larger than that hydrogen is sterically encumbering and difficult for that substance. That multidentate A-3 kind of an interaction is part of the reason that those carboxylates bind that particular surface very well. And in fact, the way that one makes a nanoplatelet of this kind is to add acetate to the crystallization. A small carboxylate facilitates the formation of that facet. Okay, so the binding of these carboxylates to this 1,0,0 surface is a very, very important aspect of cadmium selenide surface chemistry. Compare, for example, a carboxylate and an amine on that same surface. If you had to guess, if I gave you a solution of cadmium acetate with primary amines present, what coordination number do you think that cadmium ion would have? How many people would guess 3 coordinate? Nobody? How about 4 coordinate? 5 coordinate? Nobody has any clue. Well, cadmium is a 2+ ion, and it's fairly Lewis acidic. Okay. Cadmium benzoate in primary amine solution is 6 or 7 coordinate. The coordination number of cadmium ions is dependent upon the covalency of the ligands that are bound to it. So with thiolates, you'll go to 4 coordinate structures. With hard ligands like halides or carboxylates or amines, you'll go to 6 or 7 coordinate. So this thing here is very odd. But you have a ligand packing problem on surfaces, right? We know that aliphatic chains do not pack completely because they're too big for a wide area facet of 1,0,0. So at most, we're going to put down 1, sometimes none. Now you're talking about a surface that has 2 coordinate cadmium ions, when in fact cadmium would like to be 6, right? That is a very energetic situation. Chemistry happens when, like in catalysis science, if you're doing palladium cross-coupling, palladium becomes reactive when it becomes low coordinate. Okay, these are very energetic kinds of arrangements. This is a very unnatural position for cadmium to be found in, and that helps explain why a carboxylate anion would outcompete a primary amine for binding the nanoparticle. There are binding sites that are that do not match that simple monodentate thing, and where a bidentate thing is much more effective. Now, another one that's very interesting here is chloride. Remember, we talked about you could take a sample of carboxylate and add chloride to it. Chloride is not a strong base, right? Carboxylate's a much stronger base. So why does chloride displace carboxylate? The answer is that it's small. That's why. It's small, and it can do this sort of thing very well. It can bridge, and it packs in high density. All right, so the relative affinity of all these ligands is still a very strong function of the size, and you see this borne out over and over again. When considering a surface and a ligand, think about this principle of size dictating binding affinity. Okay, it's very, very important principle. Okay. Well, We looked at a series of different reactions in this section of the class. We looked at X-type exchange, where we have some EX, for example, silicon chlorine, exchanging the X's associated with some metal cation on the particle surface. The trimethylsilyl, chlorotrimethylsilane being the classic example. You could take off carboxylate and put chloride in the product. So that would be a simple X-type ligand exchange. We also talked about these reactions where an L-type neutral donor comes in and displaces a metal salt. And we call that a ligand displacement or a Z-type ligand displacement that's promoted by an L-type ligand. There's also these ionization reactions. So if you have a neutral donor like an amine, you can add an acid to it and you end up with this ion pairing situation. Okay, so that's in sort of an insertion type of a mechanism. And then there's this type of reaction. And while this is common, it is not the dominant, it is not the thing that typically dictates colloidal stability. Those types of exchanges down at the bottom there tend to be very rapid, and those ligands, not in all cases, but in many, are very labile. Okay, so I think I went through some of this. Let's just look over again. High zeta potential is very important if you want electrostatic stabilization, right? To know the charge neutrality of the crystal, you need to know the stoichiometry of the object. NMR spectroscopy is really useful here because of the breadth of the signal from bound ligands. That breadth is a consequence of heterogeneous broadening. And ligand binding strength really depends upon the number of connections that the ligand can make to the underlying crystal and the size of that object, okay? Those two principles are really very, very important. And it's that way because of the packing of surface atoms. All right. Let's see here. So I want to show you one more example of a class of materials that results from these sorts of a material whose structure is actually dictated by the surface coordination chemistry. And there are two examples of this type of thing. Magic size clusters, which are these molecules here where it's possible to get a single crystal X-ray structure of the material. And then there's another class of materials here called colloidal nanoplatelets. So both of these materials share this feature that they have molecular uniformity, okay, or uniformity that's much closer to being molecular. In fact, there are different geometries. Sometimes there are binding constants for on and off, but for the most part, you can get a single molecule. And they are that way because of the thermodynamic driving force for making these surfaces. There are other materials where you can get a single formula because of electronic structure reasons, meaning there are closed shell numbers of electrons. This is common for metals, transition metals and other metals. But for these materials, which can be thought of as salts, their structure is really dictated by the ligand shell. So people give them a fancy name. They're called magic size clusters. And this is a consequence of the fact that they disobey something called the Gibbs-Thompson rule. Okay, and we're going to talk about that as we move into crystallization theory. And Gibbs-Thompson basically says that the energy of forming a crystal, so the thermodynamics of making that crystal, drops as the crystal gets larger. So small things are more soluble than big things. Small droplets evaporate more easily than big droplets. This is a consequence of the thermochemistry of making that structure. And way down here in this length scale, where the number of atoms is few, you get chemistry that doesn't obey that relationship anymore. So in fact, there are sort of, people think, wells out here that you get particularly stable structures. And this sort of idea primarily stems from gas phase studies of like a metal vapor, but there are other examples of it. And these inorganic salts are analogous to this situation, but I think it's not really well appreciated what the differences are. Anyway, we'll come to that. But yeah, the structure of those objects is really dictated by the surface ligand coordination. Sorry, I need to think about this a little bit for a minute. Yeah, I'm not. So when studying crystals of this kind, what you'll see is very different growth behavior than when looking at a traditional quantum dot type of a system. So you've seen this graph in the past. This is taken from, I think Chris Murray made this graph for his thesis. You know, you make all these different sizes and there's this very smooth evolution of the absorption spectrum as the number of atoms in the crystals grows. But it turns out that way down at very small sizes, so these are very high energies, there's 300 to 400, that's this region down here in this chart. You don't get that kind of behavior. So this is an example of a synthesis during growth, and each one of these spectra that's acquired here is a series of different nanoparticle sizes. And you can see there are very common sizes that are separated by well-defined jumps. So take a look at this peak here that corresponds to this dashed line. In the first few minutes, you'll see a bump there that actually grows in intensity as this reaction is progressing and then begins to disappear. And it begins to disappear as the next size begins to appear, and then disappear as the next size begins to appear. And so these little particles here are actually jumping from one size to the next. They're not smoothly moving like you would see in a larger crystal's growth kinetics. So this has been called quantized growth. And you know, the explanation for why this happens is something that's still kind of debated, or different proposals have been made. But it very strongly suggests that the crystals that you see here are more thermodynamically stable than any of the crystals that are in between. Okay, so it's jumping from one well to the next well, kind of like the wells that you see on this chart there. So here's an example synthesis of one of these materials beginning from cadmium benzoate amine complex. And this particular reaction was conducted using this trimethylsiloselenide, or hexamethyl disiloselenane. And these two reagents actually react with one another at pretty low temperatures. At minus 40 degrees, the silicon will transfer to the carboxylate and you produce cadmium selenide at the end. That cadmium selenide is supported by benzoate ligands and primary amine ligands. The byproduct is that same trimethylsilyl ester. So if you monitor this reaction at very low temperatures, or compared to a typical quantum dot synthesis, which is conducted near 300 degrees, these very low temperatures, you see very well-defined jumping behavior. So at minus 40 degrees, the spectrum of this starting material is replaced with a much stronger absorbance. That process takes about 45 minutes to take place. This reactivity here is the silicon transferred to carboxylate, and the result is some cadmium selenide containing object that is a strong absorber. And then that material, if you let the solution warm from this is frozen acetonitrile, up to an ice bath, you'll watch this stuff go away and a new material appear. And again, this new material, if you warm it to room temperature, will disappear and a new crystal will appear. Okay, so this reaction is a cleaner version of this sort of jumping kinetics that I showed you on the previous slide. It turns out that if you heat this reaction hotter, this process happens again and again and again. Okay, so you can make pretty large crystals this way. And the interesting thing about this data, and there's lots of interesting things, one of the interesting things about this particular plot, but also this one, is that there are these points in the spectra where all of the spectra cross. Okay, those are called isospestic points, and they are an indication that there are two species present that are interconverting in a way that is conserved. So all the material is conserved in this reaction, and it's really just two objects or families of objects that are interconverting. Jack?
So does that imply it's just like the mechanism you said, right? Which I don't know if that's a separation.
It doesn't imply anything about the mechanism on its own. It implies that two things, or one thing converts to another thing without the formation of intermediates that accumulate. Okay, so this is an A to B.
And then the rate of like subsequent jumps, does it increase? Like, does it take longer to get to the next jump than the previous jump?
It's a function of the temperature. So it depends upon how hot you heat it. The higher you heat it, the faster it goes. So we'll talk about the mechanism a little bit more going forward. But this implies that there are this is sort of a molecular type of behavior where an A turns into a B. And that support, you could come up with two explanations, a thermodynamic one or a kinetic one. A kinetic one would be a very selective conversion. Let's say two crystals get together and stick to each other to make a new crystal. And that's the only process that happens for kinetic reasons. Maybe the one that's produced is unreactive, and the starting materials are very reactive with each other only. That could be a kinetic explanation. Another is that these two species are thermodynamic minima, and all the other crystals you might imagine making are unfavorable compared to them. So this material has been isolated and crystallized to obtain a single crystal X-ray structure of this kind. If you're a crystallographer, you'll see the R value here is fairly high. This is typical for clusters of this size. It's partly a consequence of the fact that you cannot model the organic content in this structure. Really, only the inorganic atoms are visible. If you like ellipsoids, these are at 30% probability. So it tells you that the quality of this structural assignment is mediocre, but typical for clusters of this kind. Okay. I'm getting a little bit ahead of myself here, but in fact, each of the various sizes that are grown in this experiment where you heat the solution and it converts to another size can be well described by these pyramids. Okay. Each one of these patterns that you're looking at here is something called a pair distribution function. It's an X-ray scattering experiment. And it provides a histogram of nearest neighbor distances. This is the interatomic distance on the x-axis, and wherever you see a peak, you see the peak indicates that there's a high probability of finding two atoms at that separation. Okay, so this peak here corresponds to the nearest neighbor distance in this crystal. This is the second nearest neighbor. This is the third, fourth, fifth, sixth, seventh, eighth, and so on. And so this is a fingerprint of the X-ray structure. If you take a model like the ones that are shown here, and you use that model to calculate what the PDF might look like, you can compare it to the X-ray data. One of these two is the data and the other is the model. It's kind of hard to tell them apart because the fit is very, very good. And so each one of these sizes was isolated and characterized, and you see this really smooth conversion drop in energy from the smallest one, which is that one there, and to the next one and to the next one. And in fact, this was the room temperature one. There's another one that is smaller than that. And you might imagine that one has one fewer plane of atoms. Okay, so each one of these clusters that we've isolated is growing by a single plane of atoms. That can be shown pretty well from this PDF data. All right, so back to the growth mechanism. If you look at these reactions, this object here, we determined the empirical formula of that crystal. It has 15 cadmium benzoates and 30 primary amines. And when you heat that crystal, the one that we have the single crystal X-ray structure of, to 50 degrees, you produce another object that looks like that. Now, if you do the math on the stoichiometry of this interconversion, 14 of these crystals turn into 8 of those. And in the process, you liberate 42 equivalents of cadmium benzoate. Okay. So how does that happen? Any guesses? What mechanism is that, William?
They rip each other apart, and whatever selected pieces they can get, they add to their crystal structure. That's why you liberate a large amount of compound.
So the key piece of that suggestion is that these must break into parts.
Yes.
Right? This is not an integer multiple conversion type of mechanism. You have 20 cadmium selenides, and now you have 35. Okay, so you could take 2 of these and subtract 5. Those 5 have to get in somewhere else somehow. And then down here, we're doing that again. We've got 35 cadmium selenides turning into 56. So maybe you could add this one and that, sorry, these 2 together, that gets you to 55. Oh, then you just need one more. So these interconversion, you want to ask a question? These interconversion reactions necessarily involve breaking into pieces, okay? There's no integer multiplicity here, and yet we only see 2 objects at a time. You don't see any of the intermediates, okay? All of those intermediates rearrange relatively rapidly, and the starting material and the product are very stable. Yeah.
So are all the products exactly the same size? Like they all have 35 cadmium selenide equivalents?
So it's a very, very good question. It is challenging to know what the distribution of formula are. The PDF fits to the data. If you add or subtract individual atoms from those PDF fits, the fit gets worse. Okay, so the fit supports a single structure. The smallest one, it seems like the corners might be coming on and off. So you could remove a cadmium benzoate and bind a cadmium benzoate, kind of like you would with an L-type promoted Z-type displacement reaction of the type we talked about. But to pull off more atoms than that, say to reduce the cadmium and selenium by more than 1 or 2 or 3, those are relatively large changes. It may be that there's a minor impurity of that kind of a structure. How do you prove that? Not easily. So it's hard to know.
And are you also starting with like reliably the same size crystal, like with 14 of the same size that yields 8 of what seems to be?
What I can tell you is that this type of conversion behavior strongly suggests that's true, right? Where you have tight isospecific points like that, that only really happens if the distribution of structures is really narrow and well-defined. So it's really an A and B.
So would this happen less if we were to heat to higher temperatures and get bigger and bigger crystals like we'd see.
It should, yes. Yeah, exactly. So this is not the smallest one. There's also the 0-degree reaction, right? So this is this spectrum here. That's one size smaller than the pyramid that we grew a single crystal X-ray structure of. So that thing also forms. It's slightly larger than, I think is it an adamantane? I forget. No, it's a triamantane. So imagine the bottom layer of this pyramid disappearing. That thing is called a triamantane. And that triamantane forms from something else, also with well-defined isospecific points. So the likelihood that you're going to get a distribution of structures is going to go up the bigger the crystal is. The smaller it is, the more molecular and more uniform you should expect. Okay, so a few of the things, I think I included slides on that. Yeah. A few other things about this reaction. It's irreversible. Okay, so this is a process that appears to be downhill overall. And so we think the temperature that's required here is really a matter of kinetics. Getting from this object to this object is limited by some kinetic barrier that you have to cross. And it is inhibited by ligands. Okay, this is maybe more important. The presence of ligands stabilizes these crystals. If you have a higher concentration of ligands, the crystals are less likely to grow. And this implies that the growth is a falling apart kind of a mechanism. The binding and coverage of ligands, when it increases, the structure becomes more stable. It's not a picking apart mechanism where the ligand comes on and rips parts off. So the stability of these objects is really a function of the degree to which their surfaces are coordinated. And each of these formula here, these are idealized formula. They are representative of the chemical formula of each of these pyramids within some margin of error. They correspond to one ligand per dangling bond. So we'll talk about that in just a second here, or right now, actually. So here are these different pyramids that we've characterized well. We've also characterized the next largest size. And there's a couple of features of the formula that's really interesting. One is the stoichiometry. Okay, so way down here at these very small sizes, these pyramids are entirely cadmium enriched. There's no selenium outwardly facing. They are fully covered with cadmium. That's probably a function of the cadmium carboxylate concentration in the solution. We think the corners might be coming on and off. But in the sort of idealized pyramid, you have stoichiometries that are almost totally cadmium enriched. And that ratio down here at this very, very small size approaches 2. Okay. So you can get a 2-to-1 kind of a ratio when you're really tiny, and then it drops from there. Another fun fact, this is 2.6 nanometers, getting into decent sizes. That's a sort of useful number to know. 2 nanometers is about where things begin to be molecular. And then the last thing I was talking about earlier is that the number of ligands that you see in these structures corresponds to the number of dangling bonds. And this is within some margin of error. Making these sorts of assignments of formula are very, very challenging, but it appears that all of the sites on these surfaces are coordinated by some organic ligand. There's been computational work modeling those types of structures that have reached the same kinds of conclusions, although that's pretty fresh and uncertain, I would say. In any case, there's something about what I just said should be making a light go off in your head, a flashing red light. What's the problem with this assignment? William?
Crossing over our alkane packing.
Yeah, it's written right beneath the image if you're paying attention. You can't put a ligand on every site. right? Because I told you alkane chains don't pack that well. They're too big. But this is not true when things are curved. Okay, so these are not flat facets. There are edges and corners here. And that makes more room. So these have densities of about 6 ligands per nanometer squared, which is quite a bit higher than the alkane chain packing density. But if you calculate the ligand shell volume around this, assuming these formula are correct, it's about 2 to 3-fold greater than if you just had a planar surface. So that curvature doubles the space available for ligands on this length scale. So when you are in the 2 nanometer to 1 nanometer length scale, where it's sort of, the materials are much more molecular-like and less like extended bulk surfaces, simply for steric reasons. That's a very interesting aspect of reactivity and structure in that size scale. Yeah, and just another metric that we calculated was the density of atoms in that unit, in that space, in that volume, is about 70 to 80 per nanometer cubed versus a typical organic crystal. So a crystal of rubrene or a crystal of citric acid or something like that. 100 atoms per nanometer cubed is about the packing density of atoms in space. These ligands pack with about 70 to 80 atoms per nanometer cubed density. Okay, so they're very reasonable formulas when you consider the curvature. As you get bigger, however, life changes, all right? And that makes the structure and reactivity of these types of things very unique. Oh, another one that I love diamond. It's one of my favorite materials. Density of diamond is enormous on a per atom basis, okay? It's much higher than a simple organic crystal, almost by a factor of 2. All right, so I think, yeah, one last thing about this, which I'm trying to get the group to explore, is that in a colloidal nanoplatelet, my belief is that the same forces are at play. Okay, the reason these objects are stable is that they're highly curved and you can fit ligands around them. Benzoate works very nicely because it's flat. Anything bigger than that, those start to fall apart. Okay, it's packing density that makes that possible, and it stabilizes these objects. In a colloidal nanoplatelet, the secret to making the platelets is acetate. You take a typical cadmium selenide synthesis and you dump in cadmium acetate and you'll make a platelet instead. Why is that? For steric reasons. Methyl is smaller than oleate. And it makes it possible to form this geometry in high density. You remember this computational structure, that was for a formate ligand where the hydrogen is the thing that's pointing off toward the other ligand. That's the best case scenario. Formate has other problems, but acetate's not bad. The other thing is you'll find cadmium telluride platelets are much more easily made in large area. Cadmium selenide is harder, but not too bad. Cadmium sulfide is the hardest. And that's because the lattice constant is shrinking and the steric effects are becoming more and more significant. So if you want to make very stable surfaces, you have to consider steric effects. Okay, so I think that's what I have to say for today. Yeah, lots of lessons in here. Let me just say that, having worked in this space for a long time now, I go to a lot of talks where people's intuition about, what types of ligands are present in on their surface is very naive. It's not a nice way of saying it. But what I mean is it's important to consider these ions, okay? It's very important to consider steric effects, and you should be bold in your interpretation of other people's work with those principles in mind. Okay, that would be my soapbox message about all of that, and the other was cite my paper. All right, so I think I'm done for today. Does anybody want to ask any questions? Nothing? All right, I'll see you on Monday. Take some time to go and do some of the reading, please. You're welcome.